Welcome, curious mind, to a journey that will transform the way you see the world, and the numbers within it. For centuries, mathematics has been the hidden language of the universe, describing everything from the silent ballet of planets to the intricate patterns of a snowflake. But like any language, it has its own alphabet, its own grammar, and its own set of powerful symbols. These aren't just arbitrary squiggles, they are concise, universal shorthand, each one a key that unlocks a deeper understanding of quantity, relationship, and change. As a mathematician with 2 decades of experience, I've witnessed firsthand the elegance and efficiency these symbols bring to complex ideas. They allow us to communicate profound concepts across cultures and time, making the abstract tangible and the complex manageable. In this series, we will embark on an adventure, starting from the very foundations of mathematical notation and gradually venturing into more advanced and specialized territories. My aim is not just to show you a symbol, but to illuminate its meaning, its purpose, and its real-world relevance, as if explaining it to a friend who has never encountered it before. We'll break down each symbol, explore its practical applications, and discover how it helps us make sense of the world around us. So, whether you're a complete novice or simply looking to refresh your understanding, prepare to decode the secrets of mathematics, one symbol at a time. Each continue will reveal a new piece of this universal puzzle, building your fluency in a language that speaks volumes. Let's begin to unlock the language of mathematics together. Meaning and function. The plus sign is used to represent addition, which means putting things together. When you see the word plus, it tells you to add one number or amount to another. It's one of the first symbols we learn in math because it represents a simple and essential action, combining things. Usage context. Used in elementary mathematics, arithmetic, and throughout algebra. Data analysis, and financial calculations. It's also used in everyday life, not just in math class. Practical example. Let's say you have 2 apples, and your friend gives you 3 more apples. To figure out how many apples you have now, you add 2 apples plus 3 apples equals 5 apples. This is written mathematically as 2 plus 3 equals 5. It's that simple. Addition helps us understand total amounts, and it's the starting point for all other operations in math. Meaning and function. The minus sign represents subtraction, which means taking something away. If plus puts things together, minus breaks them apart or reduces the total. It's used to show the difference between 2 numbers or amounts, like when something is removed or lost. Usage context. This symbol is used in elementary arithmetic, algebra, budgeting, accounting, and even in describing temperatures and altitudes. Subtraction is part of the 4 basic math operations. Practical example. Imagine you have 5 cookies, and you eat 2 of them. How many are left? 5 minus 2 equals 3. This means you started with 5 and took away 2, so you now have 3 cookies left. You can also think of it as comparing amounts. If John has $10 and Mary has 7, the difference is 10 minus 7, which equals $3. Subtraction helps us calculate change, loss, and balance, super handy in everyday life and critical in problem solving. Meaning and function. The multiplication sign represents multiplication, which is a way to add the same number multiple times. Instead of writing 5 plus 5 plus 5, we can multiply 3 times 5. It's a shortcut for repeated addition and helps calculate things like area, quantity, and growth. Usage context. Used in elementary arithmetic, algebra, geometry, science, finance, and even in computer programming. Multiplication is one of the 4 core math operations. Practical example. Let's say you're setting up tables for a party, and each table needs 4 chairs. If you have 5 tables, how many chairs do you need? That's 5 times 4 is equal to 20 chairs. Instead of adding 4 plus 4 plus 4 plus 4 plus 4, you multiply 5 by 4 to get 20. Multiplication is a fast and powerful tool for scaling things up, whether you're baking cookies, calculating paychecks, or building structures. Meaning and function. The division sign represents division, which means splitting something into equal parts. If multiplication is repeated adding, division is repeated subtracting or breaking things down into groups. It answers the question, how many times does one number fit into another? Usage context. You'll find this symbol all over elementary arithmetic, algebra, fractions, ratios, probability, and real-life problem solving, from sharing food to calculating averages. Practical example. You have 12 slices of pizza, and there are 4 friends at your party, including you. To share fairly, you divide 12 by 4. 12 divided by 4 equals 3 slices per person. Instead of giving out pieces randomly, division helps split things evenly and fairly. In money, if you earn $100 for 5 days of work, $100 divided by 5 equals $20 per day. Division teaches fairness, balance, and efficiency, core ideas in both daily life and deep mathematical thinking. Meaning and function. The equal sign shows that 2 sides of a math statement are the same. It's like a bridge that says, what's on the left is equal in value to what's on the right. Without it, equations wouldn't exist. It creates balance and tells you the result of a calculation or the truth of a relationship. Usage context. The equal sign is used in every level of math, from basic arithmetic to algebra, geometry, calculus, and even logic and computer science. It's the foundation of all equations. Practical example. If you say, 2 plus 3 equals 5, you're using the equal sign to show that both sides of the sentence have the same value. For example, 2 apples plus 3 more equals 5 apples. Or, if a worker earns $50 per hour and works for 2 hours, the total pay is 100. You write, 50 times 2 equals 100. Think of the equal sign as math's version of a handshake. It connects ideas and confirms they match. And function. The not equal sign shows that 2 values or expressions are not the same. It tells you that something doesn't match, doesn't balance, or simply isn't equal. While the equal sign is about agreement, this one is about difference. It helps clarify when numbers or results do not line up. Usage context. Common in algebra, logic, computer programming, and real-life comparisons. You'll see it in both simple and advanced math, especially when checking for conditions, inequalities, or errors. Practical example. Imagine you have 2 piggy banks. One has $10, and the other has $8. You'd say, 10 is not equal to 8. Another real-life example, if your friend says a pizza costs $12, but you see it's $15 on the menu. You'd point out the prices are not equal. This sign is powerful for spotting mismatches, checking assumptions, and making decisions, whether you're coding an app or splitting a bill. Meaning and function. The greater than sign is used to show that one number is larger than another. It points toward the smaller value and opens up toward the larger value. Kind of like a hungry alligator that always wants to eat the bigger number. It's a comparison tool to show which quantity wins in size. Usage context. Used in basic arithmetic, algebra, statistics, data science, and even in computer programming. Whenever you need to compare values, prices, scores, speeds, this symbol comes in handy. Practical example. Let's say you scored 85 points on a test, and your friend scored 72. Since your score is higher, we say 85 is greater than 72. Or imagine comparing temperatures. 30 degrees is greater than 15 degrees, which means it's warmer. Even at a store, if one shirt costs $50 and another costs $30, you'd say 50 is greater than 30. This symbol helps us make choices, sort information, and understand the world through comparison. Super useful, right? Meaning and function. The less than sign shows that one number is smaller than another. It's the opposite of greater than. The symbol points toward the smaller value and opens toward the bigger value, just like a little alligator always wanting to chomp the larger number. Usage context. You'll find it in elementary math, algebra, data comparisons, economics, and even coding when making decisions based on size. It's essential for comparing numbers, tracking growth, and solving inequalities. Practical example. Imagine you have 3 candies and your friend has 5 candies. You'd say 3 is less than 5. Or, if a speed limit is 60, and you're driving at 45, then 45 is less than 60, which means you're safe and not getting a ticket. This symbol helps us understand where something stands, whether it's cheaper, smaller, shorter, or slower. So yeah. Less than is like your everyday decision buddy. It's how you know when something doesn't quite measure up. Meaning and function. This symbol shows that a number is either greater than or exactly equal to another number. It means, at least, if something meets or goes above a certain level. This symbol has its back. It covers 2 possibilities in one clean statement, bigger or equal. Usage context. You'll spot it in algebra, calculus, economics, engineering, and logic. Especially when setting limits, solving inequalities, or writing conditions in programming or finance. Practical example. Suppose a job application requires you to be 18 years old or older. That's your age is greater than or equal to 18. So if you're 18, 20, or 45, you qualify. But if you're 17, you don't. Another example, if your test score must be at least 70 to pass. Scoring 70 or higher means you're good to go. This symbol is like a math bodyguard. It says, you're in if you meet or exceed the bar. Meaning and function. This symbol means a number is either smaller than or exactly equal to another number. It's the math way of saying, no more than, or, at most. So if something doesn't go over a certain value, or hits it right on the mark, it qualifies. Usage context. Used widely in algebra, statistics, economics, budgeting, and computer logic. Especially when working with maximum limits, thresholds, or conditional rules. Practical example. Let's say a ride at an amusement park has a height limit of 140 centimeters or less. That means your height must be less than or equal to 140. If you're 138 centimeters, you're good. 140 centimeters? Still good. 141 centimeters? Nope, you're too tall. Or think of a discount that applies to people who earn $30. 000 or less. If you make $28,000 or $30,000, you qualify. This symbol is all about setting upper boundaries and keeping things within safe or allowed zones. Meaning and function. The percent sign means per hundred. It represents a fraction of 100 and is used to show how much of something there is out of a full hundred. It's the universal symbol for rates, comparisons, and proportions, and it makes numbers easier to understand, especially in everyday life. Usage context. Used constantly in statistics, finance, shopping, health, science, and probability. It helps describe changes, chances, and parts of a whole in a way everyone gets. Practical example. If a store says there's a 25% discount, that means 25 out of every 100 units of the price is being taken off. So if a jacket costs $100, 25% off means you pay only $75. In school, if you get 18 questions right out of 20, your score is 90%, because 18 is 90 out of 100. Percentages also show chance. A 70% chance of rain means it's likely, but not certain, that it will rain. This symbol turns numbers into relatable, bite-sized facts, perfect for quick decisions and big-picture thinking. Meaning and function. The infinity symbol represents something that is endless, unlimited, or goes on forever. It's not a number, it's an idea. It tells you that a value keeps growing or continuing without ever stopping. You can't count to infinity, but you can describe things that head toward it. Usage context. Used in calculus, algebra, set theory, physics, and even philosophy. It's super important when talking about limits, endless sequences, space, or time. Practical example. Think about counting 1, 2, 3, 4, 5. You can keep going forever. There is no last number. That's what infinity represents, a quantity without an end. Or imagine time, even after billions of years, time still keeps moving forward. That's infinity. In math, we might say something like, as x increases, y approaches infinity. That just means the value gets larger and larger, without stopping. Infinity helps us understand the unimaginably large, and it reminds us that some ideas go beyond the limits of counting or measuring. Meaning and function. The logical and is used to say that two or more conditions must all be true at the same time for the whole statement to be true. Think of it as a team rule. Everyone must show up for the team to win. If even one condition is false, the entire statement becomes false. Usage context. Used heavily in logic, mathematics, computer programming, electronics, and set theory. It's essential for making decisions, writing rules, and building algorithms or filters. Practical example. Imagine you're setting up a login rule for an app. To enter, you must enter the correct username and the correct password. If both are right, access granted. If even one is wrong, no access. So in logic, true and true equals true. True and false equals false. False and false equals false. Another real-world example, you can go to the party if you finish your homework and clean your room. Both must happen, or no party. And is the logic gatekeeper, all boxes must be checked before moving forward. Meaning and function. The logical or means that at least one condition must be true for the whole statement to be true. It's flexible, only one part needs to work. If either option is true, or both, The entire statement is considered true. Usage context. Used in logic, mathematics, computer science, electronics, and decision-making systems. It's a favorite in coding, search filters. And yes, real-life choices. Practical example. Imagine you're planning a weekend trip and you say, "We'll go to the beach or the mountains." If you go to the beach, true. If you go to the mountains, true. If you go to both, also true. Only if you go nowhere does the statement become false. In logic, true or false equals true. False or true equals true. True or true equals true. False or false equals false. It's also used in search engines. For example, searching cats or dogs gives you results that contain either cats or dogs, or both. You get more hits, more options. Or is the symbol of possibility. If any door is open, you're good to go. Meaning and function. Logical implication shows a cause and effect relationship. It's used to express that if one thing is true, then another thing must also be true. It's written like this. If A is true, then B must follow. It doesn't claim A is true, just that if it happens, B comes with it. Usage context. Found all over logic, proofs, philosophy, mathematics, computer programming, and formal reasoning. It's a building block of if-then statements and logical conditions. Practical example. If it rains, then the ground will be wet. This doesn't mean it's raining now. It just says, whenever it rains, the ground gets wet. So, if it rains, ground is wet, white heavy check mark. If it doesn't rain, who knows? Maybe the ground is wet, maybe not. In logic, true implies true equals true. True implies false equals false. False implies true equals true. False implies false equals true. This symbol teaches us how conditions trigger results. Even when we don't know if the first part is happening, it's about the structure of truth. Meaning and function. The biconditional expresses that two statements are true at the same time, or false at the same time. In short, A is true if and only if B is true. It's a two-way street. One condition guarantees the other and vice versa. There's no one-way relationship here, either both hold, or neither does. Usage context. Used in mathematical proofs, logic, philosophy, and definitions. It's essential when setting up precise rules, equivalences, and exact definitions. Practical example. Say, you can ride the roller coaster if and only if you are at least 120 centimeters tall. That means two things. If you're 120 centimeters or taller, you can ride. If you can ride, you must be 120 centimeters or taller. So the condition works both ways. You can't just meet one side and ignore the other. Another example in math. A triangle is equilateral if and only if all its angles are equal. Both conditions must always go hand in hand. The biconditional symbol is like a double lock system, both keys must match. No cheating the logic. Meaning and function. This symbol is used to show that an item belongs to a group or set. It means this specific thing is part of that larger group. In math, we call the group a set, and the item an element. This symbol helps us say what's inside and what's not. Usage context. Essential in set theory, and widely used in algebra, logic, statistics, and computer science. It's the foundation of sorting, categorizing, and grouping information. Practical example. Let's say we have a set of vowels. The set is A, E, I, O, U. We can say A is an element of the vowel set. Yes. Or B is not an element of the vowel set. No. Another everyday example. If you're part of a book club, then you are an element of the set of book club members. This symbol teaches us how to group ideas, filter data, and organize information logically, just like putting socks in the sock drawer. Not the fridge. Meaning and function. The empty set is a set with no elements at all. It's like an empty box, technically a set, but it doesn't contain anything. This concept might seem strange at first, but it's super important in math for understanding limits, logic, and what happens when nothing fits a rule. Usage context. Used in set theory, algebra, logic, probability, and even computer science. It often appears in search results, filters, and math proofs when there's no valid answer or match. Practical example. Imagine you're looking for all green apples in a basket. But the basket only has red ones. Your result? An empty set. There are 0 green apples in that group. Or, let's say you're trying to find a number that is both odd and even at the same time. That's impossible. So the set of such numbers is empty. Even though it's empty, it's still a set, like an official placeholder that says, "Yes, we checked." And nope, there's nothing here. This symbol reminds us that nothing can still be something worth knowing. Meaning and function. The union symbol is used to combine all the elements from 2 or more sets, without repeating anything. It says, let's take everything from both groups and throw it into one big collection. It's like merging contact lists or music playlists. Everything goes in, no duplicates needed. Usage context. Used in set theory, logic, statistics, data science, database searches, and probability. It helps describe the total possible outcomes or the full scope of categories. Practical example. Let's say set A equals apple, banana. Set B equals banana, cherry. The union of set A and set B is apple, banana, cherry. We took all the items from both sets and built one big combo group. Banana was in both. But we only list it once. Another example. Set A equals people who like dogs. Set B equals people who like cats. The union is everyone who likes dogs, cats, or both. Union is about inclusion, casting a wide net to see everything you've got when you bring groups together. Meaning and function. The intersection symbol is used to find what's common between 2 or more sets. It answers the question, what do these groups have in common? It's like drawing a Venn diagram and looking only at the overlapping part in the middle. Usage context. Used in set theory, logic, statistics, database filtering, probability, and information systems. It's perfect for narrowing down shared characteristics or matching multiple conditions. Practical example. Let's say set A equals apple, banana, cherry. Set B equals banana, cherry, mango. The intersection of A and B is banana, cherry. These are the fruits found in both sets. Another example. Set A equals students who play soccer. Set B equals students who play piano. The intersection is students who do both, play soccer and piano. This symbol helps us filter, focus, and find overlaps. Whether it's shared interests, matching search criteria, or common ground in data. Meaning and function. The set difference symbol tells us what's in one set but not in the other. It's like asking, what does set A have that set B doesn't? This is subtraction for sets, removing shared elements and keeping only the unique stuff. Usage context. Used in set theory, data filtering, logic, computer science, and probability. It's a go-to when you want to eliminate overlap and focus on what's distinct to a group. Practical example. Let's say set A equals apple, banana, cherry. Set B equals banana, cherry, mango. The difference A minus B equals apple. Why? Because banana and cherry exist in both sets, so we subtract them, only apple remains. Real-life example. Set A equals all your Facebook friends. Set B equals people invited to your birthday party. The difference A minus B equals Facebook friends not invited to the party eyes. This symbol helps us refine data, spot exceptions, and understand boundaries, what's in, what's out, and what's yours alone. Meaning and function. The Cartesian product creates all possible ordered pairs between elements of two sets. It answers, what are all the ways we can pair one item from set A with one from set B? Each pair is written in order, like A, B, meaning A from the first set, B from the second. Usage context. Used in set theory, algebra, database systems, geometry, and computer science. It's also foundational in coordinate systems, like graphing points on a grid. Practical example. Let's say set A equals 1, 2. Set B equals x, y. The Cartesian product A times B is 1, x, 1, y, 2, x, 2, y. Each item in A is matched with each item in B. Another example. Set A equals shirt colors, red, blue. Set B equals sizes, small, medium. The Cartesian product gives you red, small, red, medium. Blue, small, blue, medium. That's how you list every possible combo of shirts. This symbol is the backbone of combinations, coordinate planes, and even AI training data, pairing things up to cover all possibilities. Meaning and function. The absolute value tells you the distance of a number from zero, no matter which direction it came from. In other words, it removes the sign, it makes negative numbers positive. Why? Because distance is always positive, you can't walk -5 steps. Usage context. Used in algebra, geometry, calculus, physics, engineering, and data science, anywhere distance, deviation, or magnitude matters. It's essential when direction isn't as important as how far you've gone. Practical example. The absolute value of 5 is 5. The absolute value of -5 is also 5. Because both are 5 units from 0 on a number line. Real-world example. If you owe someone $20, and another person gives you $20, those are opposites, but the absolute value of both is 20. Or say a plane flies 200 meters north or 200 meters south. The direction changes, but the distance traveled is the same, 200 meters. This symbol is like a measuring tape. It doesn't care which direction you came from, only how far you are. Meaning and function. The square root tells us what number, when multiplied by itself, gives you the original number. It's like asking, what number times itself equals this? It's the reverse of squaring. While squaring makes things grow, square roots bring things back to their original base. Usage context. Used in algebra, geometry, trigonometry, engineering, architecture, physics, and even finance, especially in risk calculations and formulas like standard deviation. Practical example. The square root of 25 is 5, because 5 times 5 is equal to 25. The square root of 49 is 7, because 7 times 7 is equal to 49. In real life, imagine a square with an area of 36 square meters. To find the length of one side, you take the square root of 36, which is 6 meters. So, square roots help you reverse engineer areas, solve equations, and measure dimensions. This symbol is like a math detective. It digs beneath the surface to find the original building blocks behind the scenes. Meaning and function. An exponent tells you how many times to multiply a number by itself. It's like putting a number on repeat. If you see 3 raised to the power of 4, it means 3 times 3 times 3 times 3 is equal to 81. So instead of writing it out long, you use a compact power notation. Usage context. Used everywhere from arithmetic to algebra, physics, engineering, finance, and data science. Exponents help describe growth, decay, area and volume, and big or tiny quantities like those in space or atoms. Practical example. Let's say you earn $2, and your money doubles each day. After 5 days, you don't have 2 times 5 is equal to $10. You have 2 is equal to 2 times 2 times 2 times 2 times 2 is equal to $32. That's exponential growth. Things grow fast. Another example. In geometry, to calculate the area of a square, you use side length raised to the power of 2. If one side is 6 units, then 6 superscript 2 equals 36 units superscript 2. Exponents are math's power-up button. They let numbers scale quickly and describe real-world change, from bacteria multiplying to bank interest growing. Meaning and function. A logarithm tells you what power you must raise a certain base number to in order to get another number. In simple words, what exponent gives me this result? If 2 superscript 3 equals 8, then log base 2 of 8 is equal to 3. Because 2 raised to the power of 3 equals 8. Usage context. Used in algebra, computer science, data science, biology, finance, and earth sciences. Logarithms help analyze exponential trends, compress big data, and even measure sound, light, or earthquakes. Practical example. Let's say a viral video doubles its views every day. Day 1. 1 view. Day 2, 2 views. Day 3, 4 views. Day 4, 8 views. Now you have 8 views. To figure out how many days it took, you'd use log base 2 of 8 is equal to 3, since 2 superscript 3 equals 8. So it took 3 days. Another example. The Richter scale for earthquakes is logarithmic. A quake that measures 6 is 10 times stronger than one that measures 5. Logarithms help us shrink massive numbers into something more understandable, turning explosive growth into manageable insight. Meaning and function. The delta symbol represents change or difference between two values. It's like math's way of saying, how much did this thing increase or decrease? It's especially useful when tracking how something evolves, be it speed, cost, temperature, or anything that varies. Usage context. Used in algebra, calculus, physics, statistics, economics, and data analysis. Delta is vital for describing trends, movement, and comparing before and after. Practical example. Let's say you had $50 yesterday and today you have $65. The change in money, delta, is 65 minus 50 is equal to 15. So, delta equals 15. That's your increase in dollars. In symbols, money equals 15. Another example in physics. If your car's speed goes from 30 km per hour to 50 km per hour, then speed equals 50 minus 30 is equal to 20 km/h. Delta tells you that your speed increased by 20. This symbol is your go-to for tracking progress, loss, growth, or shift. It's like a math-based time-lapse for any variable. Meaning and function. The derivative measures how a quantity changes with respect to another, usually, how one variable changes as time or position changes. Think of it as a speedometer. It doesn't tell you how far you've gone, but how fast you're moving at this exact moment. If a function gives you a curve, the derivative tells you the slope of that curve at any point. Usage context. Used heavily in calculus, physics, engineering, economics, and machine learning. Derivatives model motion, growth rates, trends, optimization, and anything that involves change over time. Practical example. Imagine you're driving and tracking your position over time. The derivative of your position is your speed. So if you go from 0 km to 100 km over 2 hours, your average speed is 50 km per hour. But the derivative tells you your exact speed at 1 hour, even if you were slowing down or speeding up. Another example. In business, the derivative of your revenue over time tells you if sales are increasing or decreasing right now. That's valuable insight for decision-making. Derivatives help us see how fast things shift, not just what's happening, but how sharply and suddenly it happens. Meaning and function. An integral is the opposite of a derivative. While derivatives zoom in to measure instant change, integrals zoom out to measure the total accumulation over time, space, or any dimension. Think of it as a way to add up lots of tiny pieces to understand a whole, especially when those pieces change continuously. Usage context. Used extensively in calculus, physics, engineering, probability, economics, and geometry. Integrals are essential for computing areas, volumes, distances, totals, and expected values. Practical example. Imagine you're driving and your speed varies over time. You want to know the total distance you've traveled. By taking the integral of your speed, you calculate your total distance, even though the speed wasn't constant. Another example. To find the area under a curve on a graph, say, how much rain fell over 24 hours. You integrate the graph of rainfall rate over time. If a derivative is about what's happening now, then an integral is about what's the cumulative result of everything that's happened. It's math's version of zooming out and asking, what's the big picture? Meaning and function. A limit tells us what value a function is getting closer to as the input approaches a certain number. even if a function never actually reaches that number. The limit lets us say, if we get close enough, this is where we're heading. It's how math handles situations where exact answers don't exist, or where something gets infinitely close to a point. Usage context. Limits are foundational to calculus, and essential in analysis, physics, engineering, probability, and computer modeling. They're used to define derivatives, integrals, and understand infinite behavior. Practical example. Imagine you're pouring water into a glass that holds exactly 500 milliliters. You keep pouring 0.1 milliliters at a time, getting closer and closer to the top, but stopping just before it spills. You never pour exactly 500 milliliters, but you approach it. The limit of the water in the glass is 500 milliliters. Another classic example. What happens to 1 divided by x as x gets closer to 0? As x0, the value grows toward infinity. So, the limit helps us describe that infinite growth without ever dividing by 0. Limits allow us to handle the almost, the approaching, the infinitely small, and they form the bridge between algebra and calculus. Meaning and function. A partial derivative measures how one variable affects a function, while keeping all other variables constant. It's like asking, if I only adjust this one thing, how does the result change? It focuses on one dimension of change in a world where multiple variables are at play. Usage context. Partial derivatives are used in multivariable calculus, physics, engineering, economics, machine learning, and optimization. Anywhere you have functions with more than one variable, partial derivatives help break down how each input contributes to the output. Practical example. Let's say the temperature in a room depends on time, position, and humidity. If you want to know how temperature changes over time but keep position and humidity fixed, you use a partial derivative with respect to time. Another relatable example. In baking, if the perfect cake depends on flour, sugar, and baking time, the partial derivative tells you how changing just the sugar affects the result, without touching the other ingredients. This symbol lets you explore how systems behave one factor at a time, helping scientists and analysts fine-tune results with pinpoint accuracy. Meaning and function. The gradient shows how a multivariable function increases the fastest. It points in the direction of steepest ascent. It's like a compass that not only tells you how fast something's changing, but also which direction to move to increase the result the most. Mathematically, the gradient is made of all the partial derivatives of a function, one for each variable. It's written as a vector, showing change across multiple dimensions at once. Usage context. Used in multivariable calculus, physics, machine learning, optimization, and engineering. It's essential for understanding fields, slopes, forces, and gradient descent algorithms. Practical example. Imagine you're hiking up a hill. The gradient tells you, if you want to reach the top fastest, go this way. It gives both direction and steepness. In 2D or 3D space, the gradient looks like an arrow pointing uphill on a terrain map. In machine learning, algorithms use the gradient to figure out how to improve themselves. Moving in the direction that reduces error, this is called gradient descent. So the gradient isn't just about change, it's about navigating smartly in a complex world of variables. Meaning and function. A vector represents both magnitude and direction. It's not just a number, it's a directed quantity. Think of it as an arrow. The length tells you how much. The direction tells you where. Vectors help describe things like movement, force, and velocity that can't be captured with a single value. Usage context. Vectors are essential in physics, engineering, 3D graphics, machine learning, and calculus. They're also the core of linear algebra, a powerful math branch behind computer vision, robotics, and AI. Practical example. Imagine you're walking. 5 meters north is a vector. Just 5 meters is only a magnitude, missing direction. So the vector tells us how far and which way. In physics, forces like gravity or wind are vectors. In 3D games, your character's position, speed, and camera angle are all controlled by vectors. Vectors are how math moves through space, pointing the way in physics simulations, animations, and even neural networks. Meaning and function. A matrix is a rectangular grid of numbers, arranged in rows and columns. It's used to represent and solve systems of equations, transform space, or store and manipulate data. In essence, a matrix is math's way of handling multiple values at once, compact, powerful, and structured. Usage context. Matrices are used in linear algebra, computer graphics, machine learning, economics, physics, robotics, and data science. They help model transformations, store multidimensional data, and perform complex operations efficiently. Practical example. Imagine a spreadsheet with 3 rows and 2 columns. 1 2. 3 4. 5 6. That's a 3 by 2 matrix, 3 rows, 2 columns. You can multiply it with another matrix, rotate it, or scale it, just like stretching or twisting an image in a graphics editor. In real life. In video games, matrices rotate characters and cameras in 3D space. In AI, matrices represent weights and activations in neural networks. In economics, matrices model flows of money, supply chains, or systems of decisions. The matrix is like a supercharged calculator, turning equations, movements, and data into something you can actually work with. Meaning and function. The determinant is a special number you calculate from a square matrix, same number of rows and columns. It tells you key things like: does the matrix have an inverse? Does it stretch, flip, or collapse space? Think of it as the matrix's summary value, a single number that reveals deep properties about how that matrix behaves. Usage context. Used in linear algebra, geometry, computer graphics, physics, and engineering. Determinants are vital in solving systems of equations, checking if a matrix is invertible, and understanding how space is transformed. Practical example. For a 2 by 2 matrix like this, AB, CD, the determinant is calculated as A times D, minus, B times C. So for 2 3, 1 4, the determinant is 2 by 4, minus, 3 by 1, equals 8 minus 3 is equal to 5. If the determinant equals 0, the matrix collapses space, meaning it can't be reversed or undone. In geometry, this means it squashes the shape flat. Determinants help us know whether transformations preserve space, crush it, or flip it. They're like DNA codes for matrix behavior. Meaning and function. The identity matrix is a special square matrix that acts like the number 1 in multiplication. When you multiply any matrix by the identity matrix, it stays the same, just like how 1 times 5 is equal to 5. In the identity matrix, all the diagonal entries, from top left to bottom right, are 1. All other entries are 0. This matrix represents do-nothing transformation. The original input stays untouched. Usage context. Crucial in linear algebra, computer graphics, control systems, machine learning, and any place that uses matrix operations. It's the foundation of matrix inversion, vector transformations, and even neural networks. Practical example. Here's a 3 by 3 identity matrix. 1 0 0 0 1 0 0 0 1. Multiply this with any compatible matrix, and the result is the original matrix. It's like holding a mirror to a shape, it reflects it exactly without changing anything. In 3D graphics, the identity matrix means no rotation, no scaling, no translation. It's like saying, leave it exactly where and how it is. So, the identity matrix is the mathematical equivalent of stay the same, quiet, powerful, and essential in keeping structure and stability. Meaning and function. The inverse matrix reverses the effect of another matrix. If matrix A transforms something, the inverse of A, written as A superscript 1, will undo that transformation. Just like multiplying a number by its reciprocal gives you 1, multiplying a matrix by its inverse gives you the identity matrix. In symbols, A times A superscript 1 equals I. That's the matrix version of 5 times 1/5 equals 1. Usage context. Used in linear algebra, cryptography, engineering, computer graphics, data science, and systems of equations. It's especially useful when solving matrix equations like AX equals B, where you multiply both sides by A superscript 1 to find X. Practical example. Imagine a robot arm controlled by a matrix that moves it forward and up. But now you want the arm to return to its original position. You'd use the inverse matrix to undo the movement. Or, let's say matrix A scrambles data. Then A superscript 1 unscrambles it, like a digital key to reverse the process. But heads up, not all matrices have an inverse. If the determinant is 0, the matrix is singular and can't be undone. The inverse matrix is math's reset button, undoing actions and restoring balance in multidimensional space. Meaning and function. The transpose of a matrix is created by swapping its rows and columns. In simple terms, the first row becomes the first column. The second row becomes the second column. And so on. It's like rotating the matrix diagonally from the top left to the bottom right corner. Usage context. Used widely in linear algebra, statistics, data science, machine learning, and physics. It's crucial when changing perspectives, aligning data structures, or working with symmetric matrices. Practical example. Let's say you have a matrix 1 2 3 4 5 6. Its transpose is 1 3 5 2 4 6. You took the rows and turned them into columns. In real life, imagine organizing survey data. Each row represents a person, and each column a question. If you transpose it, now each row is a question and each column is a person. It's a new angle on the same information. In deep learning and vector math, transposing helps align matrices so they can be multiplied properly, like plugging puzzle pieces in the right orientation. The transpose is a clean flip, reorganizing information without changing it, offering a new perspective while preserving all the meaning. Meaning and function. The imaginary unit is defined as the number whose square is -1. Yes, you read that right. While no real number squared gives -1, this special symbol I does. So by definition, I times I equals -1. This opens the door to a whole new world, complex numbers, which combine real and imaginary parts. Usage context. Used in complex analysis, electrical engineering, quantum physics, signal processing, and control systems. Imaginary numbers help solve equations that real numbers can't, especially when modeling waveforms, alternating currents, and oscillations. Practical example. You can't solve the equation x superscript 2 plus 1 is equal to 0 using regular numbers. There's no real number that squares to -1. But in the complex world, the answer is x equals I or x equals I. Another real-world use. In electrical engineering, alternating current, AC, calculations use complex numbers, where I represents a phase shift in voltage or current. So the imaginary unit is not just a weird trick, it's a necessary upgrade for modeling real systems that move in waves, cycles, or rotations. Math didn't get weirder, it just got deeper. Meaning and function. The modulus of a complex number tells you its distance from 0 in the complex plane. If you have a complex number written as a plus by, its modulus is calculated as square root a superscript 2 plus b superscript 2. Think of it like the length of the vector from the origin, 0, to the point, a, b, on a 2D plane. Usage context. Used in complex analysis, engineering, quantum physics, control theory, and signal processing. It helps calculate amplitudes, magnitudes, and intensity of wave-like behaviors. Practical example. Let's say the complex number is z equals 3 plus 4i. Then its modulus is square root 3 superscript 2 plus 4 superscript 2 equals square root 9 plus 16 equals square root 25 equals 5. This is like calculating the straight line distance from the origin to the point, 3, 4, just like using the Pythagorean theorem. In real life. In electrical engineering, the modulus tells you the magnitude of an alternating current signal. In quantum mechanics, it's used to find the probability of where a particle might exist. So the modulus is your measuring stick in the complex world, telling you how strong or far a number really is. Meaning and function. The argument tells you the angle a complex number makes with the positive real axis on the complex plane. Imagine plotting your complex number as a point. The argument is the direction from the origin to that point, measured in degrees or radians. Usage context. Used in complex analysis, signal processing, electrical engineering, physics, and anywhere waves or oscillations occur. The argument helps describe phase shifts and direction in these fields. Practical example. For a complex number 3 plus 4i, the argument is the angle formed by the point, 3, 4, with the x-axis. Using trigonometry, this angle is approximately 53 degrees or 0.93 radians. In real life. In alternating current, AC, circuits, the argument represents the phase difference between voltage and current, which affects how efficiently power is used. Think of the argument as the compass heading for your complex number, showing which way it points in the two-dimensional plane.
Thank you for joining me on this exploration. If you found this intriguing, please share your thoughts in the comments below. Stay tuned for our next video. where we'll uncover even more captivating stories that illuminate the wonders of our world.